Hello and welcome to Advent of Code in F Sharp, day 20, part 2. So this morning I left this day's puzzle solved part way, so we only solved part 1. And then I took some time to take a nap and have a bit of my weekend. But I started looking at part 2, and whoo boy, was part 2 a beast of a puzzle. It wasn't really very complex or complicated. It was a lot of work. You had to do a lot of groundwork to actually solve your puzzle. So I solved it eventually, and I'm not going to walk you through everything, but I'm going to walk you through like the main algorithm I designed. So maybe if you're still stuck, maybe I could provide some pointers. Because today seems to be a problematic puzzle or a hard puzzle for everyone. There's only 3,500 people that solve both parts, which is on the low end of the spectrum. It's not you, it's the puzzle. That's all. That's what I wanted to say. When we left part 1, I was rotating and flipping puzzle pieces, and we had like way too much. We had duplicates in it, so we were calculating the same configuration for a puzzle piece twice. So I did some troubleshooting there first, and it turns out that you only need to rotate or like have every rotation of a puzzle piece and then just flip all those pieces once, not like on the horizontal axis and the vertical axis, because otherwise you get some duplicates. So this was already a performance boost, but another huge performance boost was in the rotating and flipping. I used to do that for every piece, for every time I used a piece. But now in my final result, I just calculate all the rotations and flips of puzzle pieces beforehand. And it's only, 144 puzzle pieces. So before I start calculating, I just calculate all the possible rotations and flips. It takes a bit of memory, and you need to look it up by the puzzle ID or whatever, but you can do this beforehand and you don't have to keep rotating and flipping puzzle pieces when you're trying to lay your puzzle. So maybe let's go over what we did in part 1 was find the corner pieces. And we did that by finding pieces that had 2 borders and just 2 borders that matched with the borders of another piece. And actually we can use that to solve part 2. So let me draw something here. Say you have the 4 corner pieces. If you just take one and put that in the corner here, and then just loop through the entire puzzle like this, because we know it's 144 pieces, so it's a 12 by 12 square, and we're just gonna loop through it left to right, top down, like we're reading a book, and every time we will try to find the missing piece. Yeah, so I have my lookup table of a puzzle piece and all its rotations. So a puzzle piece and all its different rotations and flips, another puzzle piece with all its rotations and flips. So there's like this big lookup table I use. And then every visit, I take a look at what's above me, but in the first row that's not really interesting, and what's to the left of me. So for example, let's take another one. Let's take this one. What's above me, what's to the left of me. If you do this for every place in the puzzle, you will end up matching all the borders, so this works just fine. So you always look up in the already laid part of the puzzle. So this is the already laid part of the puzzle, everything up this thing. And you look up the puzzle pieces right above you and to the left of you. If you find none, cool, you're on the border, you don't need to do any matching. But if you are finding other puzzle pieces, you just grab the respective borders. So for this upper one, let's take another color. For this upper one, you take the lower border. For the puzzle piece to your left, you take the right border. And then you just go through the dictionary or through all your puzzle pieces, and you find a puzzle piece that has like these 2 borders. So maybe it's in here. So the top matches and the left matches with what we just found. Then we know, okay, it's a puzzle with this ID, and it's this rotation or flip that needs to be here. This is making some assumptions, like the first match we find will be the correct one, because I didn't even implement backtracking or like trying multiple options if there were. I just did a greedy, just match the first match, but it seems to work. And this was like part 1, building your puzzle. And then you have your puzzle, and you have like every puzzle piece and its orientation. Next step is removing the borders. So I trim every matrix, just remove the outer borders, and then you end up with the small pieces. Then next step, I merge them together. So then you have a big single matrix, and we're falling off the screen here. So let me do this. So you have a big matrix, which is a puzzle. And then we need to look for sea monsters, which was a also interesting part. And we could you might need to rotate your puzzle to find the correct configuration of the puzzle. So you might rotate it or flip it, and only one of the 8 or whatever configurations contains sea monsters. So I use again the same algorithm to generate all the possible rotations and flips of a puzzle piece. This means we end up with, don't remember, 8 puzzles or something like that. And then I just start looking for sea monsters in each of those 8. And then you find the sea monsters. You can calculate how many of the spaces are, what was it? Rough waters, and then you just subtract the number of monsters or pixels that make up a monster, and that's how you end up with 2 gold stars. Let's see if I can go over the code, or if there's something else worth mentioning. So yeah, we have basic operations like rotating, flipping, trimming borders, merging all the little puzzle pieces together into a single matrix. Parsing was for part 1. These are the get me the right side of a puzzle piece or the left border of a puzzle piece. So these are also interesting. This is the function that generates all the possible rotations and flips. So it's pretty declarative if you write it like this. You can see it's the tile itself and a rotated and a 180 rotation. And then all those, we take those pieces, but also flip them. So that's a 1, 2, 3, 4 times 2 is 8 configurations for every puzzle piece. So yeah, it's a bit of calculation. Find corners was for part 1. We're already at 100 lines of code, and F# is a very dense language, so this was a real crunchy puzzle. This data structure is what I do to keep my lookup table. So it's the mapping a tile ID to all the possible rotations and flips. Yeah, this is finding the top left piece, which was a bit trickier than I anticipated. So we already had the corners, but then you have to rotate the piece so the borders line up, or at least my approach needs that. And then we generate all the coordinates we still need to visit. So we know the top left, but every other coordinate in the puzzle we need to fill in. And that's what I do here with tasks. And then I just do the good old folding again. So I fold the currently built puzzle, so everything in the top left half of the puzzle. And I just start placing piece after piece after piece from this lookup table. And this is the logic. So I take a look above, I take a look at the left, as I explained. And depending on what I find, I try to look if the borders match, or if I find a puzzle piece or one or more puzzle pieces that have these 2 or 1 borders. So yeah, that's how you complete your puzzle. Then you just trim the borders for every puzzle piece. That's what I do here. And then you merge every puzzle piece together into a single bitmap. That's what I do here. And then how did I find monsters? Well, I mapped the pattern. So that's this thing, the monster, the sea snake. I mapped that to coordinates where these symbols appear. So then I have like a list of relative positions where these symbols have to appear. And if I visit a coordinate and I look at the relative coordinates of the sea monster, if there's a match on every of those coordinates, we found a sea monster. So that's what I do here. So I look at every possible rotation of the final puzzle, and then I just loop over every XY coordinate in that puzzle, and I see if this location like matches with the monster pattern, and that's how I calculate the number of monsters. And if you know how many monsters there are, you know how many rough waters there are in your puzzle, then you can calculate how many rough spots remain that are not monsters. And there you go. Then you end up with a reasonably fast algorithm. But the problem today was not in computation time, it was in actually doing the legwork. So writing the combination, the rotation, it's a pretty rough puzzle. I hope next week will not be puzzles of this caliber, because I sure had my work cut out for me. So yeah, that's day 20 part 2 in F sharp. Sorry for not showing you the code, but this would have been a video of, I don't know, 2-3 hours, because it was really a lot of noodling around and writing very dense F sharp code. Not the proudest code I've ever written, or I'm not the proudest of it, but it was a fun puzzle. Let's just hope that the next days are a bit more on the lighter side. So see you tomorrow for next puzzle.